that really, there's not too much to memorize in this one. There's really only one formula you have to remember, and that's it. So it's just a matter of reworking that formula to fit the question you're being asked. So, for instance, just for grins and giggles, what is the formula that I'm talking about that you have to, everyone should know?
PV equals nRT.
There you go. That's it. Good old PivNert. So if you can remember PivNert, that's really all you need to remember. And then, like I said, it's just a matter of moving just basically rearranging the formula to fit the question. So here's a classic example right here. So you're given a question about nitrogen, which is a gas, as we all know. So we have, this is our volume, and then this is our pressure, and then this is our new pressure. So you could try and remember which particular law it is that relates volume and pressure and fit it in that way. Or you could just go to good old PivNert and see that basically what we have to do is relate volume and pressure. So our volume is going to change, our pressure is changing, but everything else is remaining constant. So basically this means that P1 times V1, so our initial pressure and our initial volume are going to equal NERT, right? And so NERT is all going to be constant. The number of moles don't change. R doesn't change because it's a constant. And T doesn't change because it's doesn't change here either. So we know the PV equals P1 V1 is also going to be equal to P2 V2 because they're both equal to the same thing. P times V is equal to nRT. Well, if N doesn't change and R doesn't change and T doesn't change, then they have to be equal to the same thing. And so basically we have just derived the law, PV P1 V1 equals P2 V2, and we're done. So basically now all we need to do is convert these things to units we can deal with. So liters is liters. So V1 is going to be 22.5 liters. And we don't know what V2 is going to be. That's basically what we're going to be solving for. Equals V2. Now, what is P1 going to be? What's the initial pressure?
$748 mmHg.
What does mmHg stand for?
It's something with mercury, but I just don't know what the mm is.
Millimeters.
Millimeters. Yeah.
It's actually the initial way of measuring pressure was to have a tube filled with mercury, and at the top of the tube there would be a vacuum. So there'd be a vacuum at the top, and then basically you would measure the pressure, the atmospheric pressure, by how high the pressure pushing down on that column of mercury would make it rise up in the tube. And so there's still like one of these old pressure indicators at Skyline. And so you can actually measure the pressure in the lab. So that's basically what it is. If you get the pressure in off the weather report, basically that's given in inches of mercury, which is basically the same thing. You're just converting millimeters to inches. So there's one of two things we can do here. How many, we can convert it to atmospheres. How can we convert it to atmospheres?
You can divide by 760 millimeters of mercury.
Right, 1 atmosphere is equal to 760. So we can go 748 millimeters divided by 760 millimeters is pretty, and these numbers are all going to be really close to 1. So 748 divided by 760. So 0.984 atmospheres. So that's our P1. So P1 is 0.984 atmospheres. Now, what is our P2? What is the second pressure? Our initial pressure was 748. What's the new pressure?
0.9539.
So that's, you've taken 725 and divided it by 760?
Mm-hmm.
Okay. So what was it again?
0.954.
954 atmospheres. Now, the dirty little secret here is that you didn't need to do that. We didn't actually need to divide. We didn't need to convert these things to atmosphere. Why? Because if you look at the units here, I've got atmosphere liters, and over here I've got atmosphere, and this is in liters. If I had just kept this in millimeters of mercury, oh, sorry, 748, oops. That would have been just fine. Because basically all we're doing is dividing both sides by 760 millimeters. So we didn't really need to do that. But it's probably not a bad idea. If you're not using R, if R doesn't show up in the calculation, then you don't really need to change it. We need to change it when we're dealing with R, because R basically, the form of R, the constant that we're normally dealing with, one of the units is atmospheres. And so we would need to convert to atmospheres to cancel that. But here we're not dealing with R, so we can just leave it. So it's just remember that it's usually a good idea to convert to atmospheres, but it's not always required if you're not dealing with the gas constant. So now all we have to do is solve for V2. So V2, to solve that, we just divide both sides by 0.954 atmospheres. So divide that side by 0.954 atmospheres. And you can see this is where your units would cancel out. So if we had millimeters on both sides, we would have canceled out millimeters on both sides. So V2 is just equal to 22.5 liters times 0.984 divided by 0.954. So what is V2?
$23.21.
23.21. What in our unit?
Liters.
Liters, right. So how many significant digits should we put in our answer?
3.
3. So what's our actual answer?
23.2.
Yep, exactly. 23.2. Now, take a look and see if that makes sense. So our pressure, our new pressure, P2, is actually less than the initial pressure. So if the pressure goes down, what happens to the atmosphere? What happens to the volume?
Goes up.
Goes up, right? So if I have a balloon, if I have like a 22 liter balloon, and I've got it in a bell jar or something where I can change the atmospheric pressure. If I pull some of the air out and reduce the pressure, that balloon gets slightly bigger. And if I take it to a vacuum, it gets really, really big and eventually blows up. But the opposite occurs. If I pump more air into it and increase the atmospheric pressure, that balloon is going to get smaller. So that makes sense. So our pressure went down, so our volume definitely had to go up. So the thing that's kind of confusing, so what's confusing about this question? Read the question. Is there a problem? There's a word in there that doesn't belong. You see what it is?
The if.
Nope.
The constant temperature.
Nope.
Compressed.
Compressed, exactly. Is this gas compressed?
No.
It's expanded, right? It's actually expanded. And so if you expand something, the pressure goes down. If you compress something, the pressure goes up. So if I have a certain volume of gas, like in a cylinder or something, and I put work into it and push the cylinder down, that volume is compressed and the pressure inside the cylinder goes up. So it's actually not compressed. That's it's expanded. All right. So let's just do a couple of these and I'll just send you off to do them on your own. So let's look at this one. Oh, basically the same question, only this time, instead of changing the pressure, instead of changing the volume, we're changing the pressure. So again, our old good friend Pivnert. And so we have, so we have P1 and V1. And so we're changing, what are we changing here? We're changing, what is changing in this situation?
The volume.
So the volume is changing, right? Is there anything else changing? So we're going to pressure. So we have P1, we have V1, and we have P2, and we have V2. What else changes? So the temperature, you said that so we know that the volume changes. So yes, the volume is going to change. Anything else?
The pressure.
The pressure is going to change, right? What about, so again, we ask, do the number of moles change? No. R is never going to change, and temperature isn't going to change either. So we're stuck again with the good old P1 V1 equals P2 V2. It's exactly the same expression we had before. So we can basically plug the same information in this time. So what is P1 going to be?
$205
205 what?
kPa.
What does that stand for?
I don't know.
Kilopascals. As another, genius Frenchman named Pascal came up with that particular. There's lots of different ways to measure pressure. There's lots of different ways to say it. There's mercury, there is atmospheres, there is pascals, there's millipascals, there's all sorts of kilopascal. There's like lots of, torr is another way of expressing it. So there's lots of different ways to measure pressure. So this is our P1. What's our V1 going to be?
Four liters.
Yep, 4 liters. And so P2, what's P2 going to be? We don't know what P2 is going to be, right? Because that's the question. What is the new pressure? So we don't know what P2 is. What's V2? What's our volume after?
12 liters.
12 liters. So again, you can see that we don't have to convert kilopascals to atmospheres to do this problem, because we have liters on one side, we have liters on the other side, we have kilopascals on one side, and we're going to have kilopascals on this side. So we don't really need to do anything. The only time you would have to convert that is if 1, R was involved, or 2, if the question asked you what the pressure was in atmospheres. And this question does not ask you that. So we can just quickly just go right ahead. And how do we solve this problem? What do we do to both sides of the equation to isolate P2?
You divide 12 liters by both sides.
Yep, exactly. 12 liters, 12 liters. Liters cancel out, and I am left with this particular unit. So what will P2 be equal to?
68.5 kPa.
68.5 kilopascals. And that makes sense because remember, P and V are related to each other. So if the volume goes up by a factor of 3, what's the factor that the pressure must go down by? If my volume goes up by a factor of 3, that means my pressure has to go down by a factor of
3.
3, exactly. So because we multiply one by the other, they're inversely related, right? So if P goes up, V's got to go down. So when we multiply them together, you get the same thing. So that's how they're related. Pressure goes up as volume goes down. Now, remember, since we have, look at good old Pivnerd, this shows you the other relationships. As N goes up, what's going to happen to both P and V?
They go down.
Mm-mm. If I double N, what must happen to the PV side?
They go up.
It's got to go up too, right? So if I multiply the NERT side by 2, well, then I'm going to have to multiply the PV side by 2 as well. So if N goes up, the product of P and V have to go up as well. So either P goes up or V goes up, or they both go up, but they have to go up. Same thing is true with temperature, right? If I increase the temperature, then my product of P times V has to go up as well. So either the pressure goes up, the volume goes up, or they both go up. Or if the pressure goes down a little, then the volume's got to go, way up. So that's how we know, based on which side of the equation, what the relationship is. Since P and V are on the same side of the equation, they're inversely related. Since P and number of moles are on the opposite sides of the equation, that means they're directly related. Same with temperature. They're directly related. If one goes up, the other one has to go up as well. So that's why I don't like to sort of memorize all the, like Boyle's law, Charles' law, and all that stuff. I can't remember which is which, but I'll always remember PV equals nRT. You might as well just have it, tattooed on my brain. All right, let's just do one more. Here we go. So what pressure, oh man, we're not going to be doing any, we need a good PivNerd question. So I'll leave that one. That one. Need a good piv. There we go. So now we're changing a couple of different things. Now we're going to need to. Now we're going to need to do some serious piv nerding. So here's my piv nerd. So this time we've got P1, T1, and V1. So there's three things changing this time. So what's P1 equal to? What's the initial pressure?
740 millimeters.
Yep, it's 740 millimeters. What is T1?
45 degrees Celsius.
Mm-hmm. 45 degrees C. And the pressure, and the volume, V1.
106.0 liters.
106.0 liters, right. So that is our P1, T1, V1. What is our P2, T2, and V2? What's the second pressure after?
780 millimeters.
Yep, so that's our P2. What's our T2?
20 degrees Celsius.
Yep. 20.0, right? And our volume, we don't know. That's what we're solving for. So we're solving for V2. Okay. So in this situation, N is staying constant and R is staying constant. So basically, we're just looking at the relationships between pressure, volume, and temperature. So in this instance, P1 times V1 is equal to a constant, NR, and T1. Meanwhile, so what I can do is divide both sides by T, right? And get and then I'll get a constant. If I divide both sides by T1, then I get NR. So I can get rid of the T1 on this side. So P1 times V1 divided by T1 is equal to a constant. That tells me that, that tells me that P2 times V2 divided by T2 is equal to a constant as well. And therefore, these two things are equal to each other. So those two things are equal to each other. Do you see how that works? It's just a little too confusing.
No, because you just divided the NRT side by T and then to put that T on the other side, right?
Right, exactly. So I'm basically, all I'm doing is looking to see how I can get a constant. Now before, when just the pressure and the volume changed and everything else was constant, then P times V was a constant because it gave us nRT, and that's not going to change. In this instance, N doesn't change, but T does. So how do I manipulate my PivNerd to make sure that I've got a constant on one side? How do I do that? By dividing each side by T. And so since The initial pressure times the initial volume divided by the initial temperature gives us a constant. Well, then that means when I change the pressure and the volume and the second temperature, those things have to give me a constant too. So this is how I can relate the two to each other. So P1 V1 divided by T1 equals P2 V2 divided by T2. And I didn't have to memorize anything to get to that. So now we just use that. We just plug in our values. So let's just go ahead and do that. Where is my eraser? Oh, there it is. Oh man, I'm erasing all the information. Oops, never mind. Okay, so my P1 is 740 millimeters. My V1 is 106 liters. And my T1 is 45 degrees. So that is going to be equal to my second pressure, which is 780 millimeters, times the new volume, we don't know what that is, V2, divided by the pressure. Oh, wait a minute, divided by the temperature, which is 20.0 Celsius. So there is a problem here. I can't, before I could mess around with the not changing the pressure units. Can I do the same thing with the temperature units?
No,
Or do I have to change those?
we need to convert to the Kelvin.
How come?
Because
I'm not dealing with R. Why do I have to have the right units?
because the temperature in the nerd is Kelvin.
Mm-hmm.
So I think we need to convert the Celsius to the Kelvin.
We do, but why do we have to? You're right. We do have to convert to Kelvin. But why do we have to do that?
I'm not sure.
Okay. So according to this, we have basically doubled the temperature, more than doubled the temperature from 20 degrees C to 45 degrees C. Have we actually doubled the temperature? Really?
No.
No, that's right. We have not. We've not doubled the temperature at all, because the difference is Celsius is not an absolute scale. It's not absolute. It's relative. What's it relative to? It's relative to water. It's relative to the freezing point of water and the boiling point of water. The freezing point is 0. The boiling point is 100. So in actuality, we haven't doubled the temperature at all. Only Kelvin is an absolute scale, because it starts at 0 and goes to, wherever it goes to, millions and millions of degrees. But that's an absolute scale. If we go from 20K to 40K, we have doubled the temperature. If we go from 20K to 200K, we've increased the temperature 10 times. That's not true with Celsius and Fahrenheit, because they're not absolute scales. They are relative to something. So that's why you're absolutely right that we need to change to Kelvin, but that is the reason, because Kelvin is absolute, Celsius isn't, it's relative. And so if we were to do this calculation with Celsius, we'd be way overstating the change in temperature, because we're not changing the temperature by a factor of 2. We're not even coming close to that. So we're only changing it by the difference in Kelvin of 25 degrees, or 25K. So the absolute change is the same, but the relative change is hugely different. So what's the relative change here? Oops, let me go back. So the relative change is 25. What's the absolute change? Needs to be reflected in Kelvin. So how do we convert to Kelvin? We need to get rid of 45 and 20 and replace them with Kelvin. So what's 45 degrees Celsius in Kelvin?
318. 318.
318 K. So how did you do that?
I added 273.
Right, so you either add 273 or you can add 273.15. Ah, someone's at the door. So generally, I usually use the 273.15, but because I've got 4 significant digits in my pressure, so I might as well go ahead and just, it doesn't hurt to add the 0.15. I don't know how Professor Elf feels about it, but I use as many significant digits as I can. So I will change that to 318.15. So what is going to be my new temperature?
$293.15
Yeah, right. And so you can see there's a big difference between dividing 45 by 20 and dividing 318 by 293. The relative change is huge when it's in Celsius, but the relative change is tiny when it's in Kelvin, because we're only raising it by what, 10%, if that, maybe like less than 10%. So that's not a big change in temperature when it goes to Kelvin. The other reason we use Kelvin is because what is it about changing the temperature that makes the volume bigger, or the pressure gets larger? What's actually occurring on a microscopic level to make that happen? Have you reviewed that?
Does it have anything to do with the excited state?
No.
Okay.
No. Does have something to do with the molecules, but not the excited state. That's an electric thing. That's like when you're adding energy and the electrons move. This doesn't have anything to do with. It's one of the few things in chemistry that doesn't involve electrons.
Is it because like molecules expand when they're heated?
The molecules themselves don't expand. It's something the molecules are doing that makes the volume expands. Yes, the volume expands when the temperature goes up. The molecules themselves don't expand, but you're getting warm.
The molecules move faster, don't they?
Bingo. Yes, exactly. It's the kinetic theory of molecular movement, that if you increase the temperature, molecules start moving faster. So as they move faster, they are going to hit the sides of the container more frequently because they're moving faster. So they have more chances to hit the sides of the container. Well, when they hit the sides of the container more frequently, what happens to the pressure?
Pressure increases.
Pressure increases. In fact, that's the only thing that increases or decreases pressure, is how fast are the gas molecules hitting the sides of the container. If they're hitting it more frequently, pressure goes up. If they hit them less frequently, pressure goes down. Same thing with volume. If the pressure is constant, if you have a balloon and you heat it up, well, the molecules are going to be moving faster, and they're going to be pushing against the sides of the balloon a lot more frequently. Well, if you allow it to expand, that's what it's going to do. It's going to expand because they're hitting the sides of the container, and they'll keep hitting it and keep hitting it and keep hitting it until the pressure inside and the pressure outside are the same. Once the pressure inside and outside are the same, the volume will stay constant. So that's why we use Kelvin, because Kelvin gives us a description of what happens to the speed of the molecules. Because what happens at 0 Kelvin to the speed of molecules? In fact, what happens to everything at 0 Kelvin?
Everything stops moving.
Everything stops moving. Everything. So there is absolutely no movement at 0. And so that's why it's 0, because nothing's moving. And so if nothing's moving, there is absolutely no pressure at 0, because there's no molecular movement. The minute we start increasing the temperature from 0, there's some small amount of molecular movement, and then pressure starts to increase. And it's directly related to how fast they move. So here, now we can just basically solve for V2. All we have to do is multiply each side by 293.15 K and divide by 780 millimeters. Why we don't have to change the millimeters is because, excuse me, the pressure scale is absolute too. It goes to 0 and then increases to whatever it is. It's not like we need to add some number to the pressure in order to convert it to atmospheres. We just divide by something. So the difference between 740 millimeters and 780 millimeters is exactly the same as the difference if we converted both of them to atmospheres. It makes no difference because we're doing exactly the same conversion to both. We're not adding anything. When we're dealing with Kelvin, we have to add something. The minute you add something, you can't divide them. So we just get rid of this, get rid of this. Millimeters cancel. We got them on top and bottom. Kelvin cancels. We got that on top and bottom. And then the only unit we have left is liters. And that's what we want, because the question was, what will V2 be? So what's V2 going to be in this?
92.66.
92.66 what?
Liters.
Liters, right. So how many significant digits do we give?
It's 4, right?
Is it?
On the question, they're 4.
On the
Or-
question it's 4? Where? On the question it's 4? Where?
The liters and the. Oh, it's 3. Actually, I don't know.
No. I mean, you're right. It is.
I don't know if we're using the Celsius from the.
No, it is. No, you're right. You're right. Because when we convert Celsius to Kelvin, we then have 4 significant digits. You're absolutely right. So this would be our answer. Because when we take 20.0 and we add 273.15 to it, what do we get? We get 4 significant digits then. So you're absolutely right. So 92.66 liters. Excellent. Yeah, that part's tricky. That part's a curveball. All right, you want to do one more, and then we'll. You guys pick out which one you'd like to do next, and you can go off. Hopefully, everyone has the recitation by now.
Can we do 11?
Sure. 11. Ugh, how many molecules? This question's got Avogadro's. I hate Avogadro's number, but we'll do it anyway. Okay. Avogadro's number is overrated. That's just my opinion. He did a lot of other great stuff. In fact, Avogadro is the person. What's Avogadro's contribution to the gas laws? Anyone know? It's one of the laws.
Does it have to do with the volume?
Mm,
I don't remember off the top of my
Doesn't he
head.
have an
That's why.
it did have something to do with the volume. But what did he show that volume was related to?
Gas.
It's always related to gas. Everything's a gas, man. But what did Avogadro show was related to the volume?
Oh, mole.
Moles, exactly. He's Captain Moles. And so, yeah, he was the one who showed that V1N1 and V1 divided by N1 is equal to V2 divided by N2. So, because he was basically doing some experiments that showed if he produced twice the amount of moles of gas in a tube, that the volume was exactly twice as much. So he was the one who came up with that. All right. So we have got this time we're actually going to have to use the whole PivNert thing. So here's my PivNert. Because we're not changing anything. Basically, we have to figure out molecules. So because we're trying to figure out molecules, we have to figure out what everything else is first. So what's our pressure?
P.
What is it? What's our pressure here?
As in the variable P.
Yep.
650 millimeters.
650 millimeters of mercury. And our volume is 2.5. And our temperature is 50.0 degrees C. So we have a P, we have a V, we have a T. R is a constant. So basically, what is it we're solving for?
Today.
Moles.
Solving for moles, right? That's really what we're solving for. So in this instance, we're going to need to convert our units because we're now dealing with R. So the first question we've had to deal with R. So R is 0.0821. Anyone remember what the units are?
Liters ATM over moles Kelvin.
Yeah, atmosphere liters over mole Kelvin. It's a weird number. So we have to convert to atmospheres. We need to convert to liters. We need to convert to K. Well, we already have liters, so we need to convert millimeters to atmospheres. So remember, to do that, we multiply by 1 atmosphere is equal to 760 millimeters of mercury. And then to convert our temperature, we add 273.15 K. So what are we going to plug in for pressure here?
That would be 0.855 ATM.
Okay.
Oh, 855.
Oh, wait a minute. 9855. Is that it?
No, just 855.
Oh, 855. Okay. Times, and our volume's 2.5 liters. And that's going to be equal to N times, and then, so now we plug in R. So 0.0821 atmosphere liter mole Kelvin times, and then our temperature. So what's our temperature going to be?
323.15.
300 what? 333?
323.15.
1.5. Okay, right. So then to figure this out, we divide both sides by R and T. So then I just move R and T over to the other side. With 0.821 atmosphere, liter, mole, Kelvin times 323.15 K is equal to N. All of this nonsense is equal to N. So now I look and see what can I cancel. So I've got atmospheres on top and bottom, so that can go. I've got liters on top and bottom, so that can go. I have got, basically I've got K, and then I'm dividing by K, so I can get rid of K. So the only thing I have left is I'm dividing by 1 over moles. So if I'm dividing by 1 over moles, what's that equal to? 1 divided by 1 over moles, what is that?
Moles.
It's moles, right. So now so 0.855 times 2.5 divided by 0.0821 times 323.15. So that gives me N. So, and it gives me the unit. So how many moles is that?
0.081 moles.
So give me as many significant digits as you can, because we haven't got to the end yet. So remember, do not round your answer till you get to the very end. So just spit out all the numbers you got. So 0. What?
0, 8, 0, 5, 6, 7.
That's probably enough. Okay. Moles. So we're not done though, right? Because the question wasn't how many moles, it was how many molecules. So we still need to do one more unit conversion. We need to convert moles to molecules. How are we going to do that? We need to multiply that by something. Need to multiply that by something that gives me molecules at the end. So I want molecules on top.
Avogadro's number.
There you go. I want molecules on the top and I want moles on the bottom. That way I cancel moles and I'm left with molecules. And what's Avogadro's number?
6.02 times.
6.022.
Oh.
Yeah. Times what?
The 23rd.
23rd. That's right. So that's the other contribution Avogadro gave us. So 6.022 times 10 to the 23rd molecules per mole. So now I get rid of moles. I'm left with molecules. That's my answer. So what's 6.022 times 10 to the 23rd times 0.080567? Yeah.
I might have input it into my calculator wrong, but is it 4.8517627?
So 4 point what?
851.
851 times what? 10 to the 21st?
22.
Is it? Okay. Yeah, no, that makes sense. Yeah, 22nd. Molecules. Yeah, if you ever wondered how to do that, and then we look and see how many significant digits we should present this answer in. How many significant digits should we use?
Two.
2, right, because we have a 2.5 liter flask. So I would round that to 4.9 times 10 to the 22. So if you ever wonder, like, let's say you don't have a scientific calculator like me, because I'm dumb, I don't know how to use one. And you wonder, how do I figure this out? You can just change this to 60.22 times 10 to the 22nd. And then take your 60.22 and multiply it by 0.08. And that should get you at the single digit before the decimal place. So 60 divided by 60.22 times 0.08 should give you 4.85. And then it'll be the same power. That's the little trick I use when I don't have a scientific calculator. So there's your answer there. So if I was given the, I would never ask this question because I don't like Avogadro's number, because we can't measure molecules anyway. So yeah, it's a big number. There's a lot of molecules. So what? The number of moles is more important, because we can go right from moles to grams and all kinds of like things we can really use. Molecules, I guess there's, sometimes like the number of molecules is good to know, but usually it isn't. Usually moles are a lot more important. So I'll get off my soapbox for a minute. All right, so what I'll do is I will break up people into groups, and then I will come around and see how everyone's doing. But as you see, these things are pretty straightforward. It's just if you can manipulate PV NRT, you're gold. And just remember that if your temperature always needs to be converted to Kelvin, always, always, always. Pressure, if you're not dealing with R, you're fine without changing it. If you're wondering, you can always change things to atmospheres, and then you won't have any problems. Okay. So let me get some breakout.
Sorry, I don't have the recitation sheet or your recitation sheet. I'm from Schubert's section. So,
oh, okay. Yeah, there's a link in the chat. You see it?
You'll have to drop it again. I came a little bit later because I guess I didn't know that my professor wasn't having it today. Thanks, Sean.
Oh, John did. Okay.
All right.
Yeah. There you go.
Got it.
No worries. Good to have you. Is that Benjamin?
Yes, sir.
Okay. Good to have you. All right. Here we go. So I'm going to start it up, give you some time to work, and then myself and the other Benjamin will come around and see how you're doing.